What are the limitations? A sensor can either view the north side of it, or the south side of it, or the east side or the west side. So a sensor can choose one of its direction to view. Similarly for all the sensor. Now our objective is to view the entire target, maybe the two target here. So if you see this diagram, there are 6 sensors and there are 2 targets. So if I assume that X3 switch on the north side of it, it is an wastage of energy because through north side of it, it cannot see any target or it cannot cover any target. If it goes for the east side, then it can trace a part of the target. That is the front part of the target, not the back. If it says the south side, it cannot trace anything. Similarly, if it says the left side, that is the west side, then it can see the one of the target. So if I assume this sensor X1, X2, X3, X4, X5, X6 are the variables. These sensors, let us assume these sensors are the variable. Then this variable can have value east, west, north, south. It can either choose east, it can choose either west, it can choose either north, it can choose either south. So the domain of variable is east, west, north, south. আমি এটা এখন ইউজ করছি না আমি বাড়িতে যাব এখানে ও আর এটা পারি না হ্যাঁ এটা ঠিক আছে so east west north south, so the domain values are east west north east west north south. For example, you see, so if I consider this target, for this target there are 3 sensor X1, X3, X5, X1, X3, X5. Now, what can be the possible number of combination? It can be 4 to the power 3, because each variable can have the value east, west, north, south, 4, and there are 3 variables X1, X3, X4. So it can be 4 to the power 3. That many number of combination will be there. Now you see, to capture this target, the combination is south for X1, for X3 it is west, for X5 it is north. If we use this combination for X1, X3, X5 for these 3 sensor, if we use this combination, then my condition will be satisfied. All the portion of the target will be covered. Using X3, this portion of the sensor of the target will be covered. For X1, this portion of the sensor will be covered. For X5, this portion of the sensor will be covered. This portion of the target will be covered. So using the sensor X1, X3 and X5 with the combination of south for X1, west for X3 and north for X5, this target will be covered and that will be satisfied. So this is called constraint satisfaction problem. So this is the combinations of X1, X3, X5 which can satisfy my constraint. The constraint is to track this target. Similarly for this one also, you can do that. Now, constraint satisfaction problem. If we write formally the constraint satisfaction problem, it composed of variables. It can be have n number of variables, x1, x2, x3 dot xn. It can have domain of the variable. That means any variable, for example x1, can choose any of the values from this domain. Variable x2 can choose any of the values from this domain, d1, d2, d3. Similarly for xn. So for this particular example, if we assume this particular scenario, the left scenario, then there are three variables, x1, x3, and x5. And the domain east, west, north, and south. The domain will be east, west, north, and south. And the variable is x1, x3, x5. So x1 can choose any of the values from the domain north, south, east, west. Similarly, x3 can choose north, south, east, west. x5 can choose any of this, north, south, east, west. Now, what is the constraint? We are writing the constraint in the formal form. Constraint C is a collection of C1, C2, C dot Cm, where a constraint Ci is a subset of domain. It is a cross product of the all domain values. That means for this particular scenario, the x1, x3, x5, this is the satisfaction. This satisfies my requirement. For the remaining cases, for remaining all the combinations, this is not satisfied. So if we take all the values of north, this one is north, this one is north, this one is north, this will not be tracked. So the value is null, or you can put as infinite value, which we cannot afford. North, northeast, this one is north, this one is north, this one is east. Again, we cannot trace. So the constraint is that combination which is not feasible, or which through that you cannot achieve your goal. So if we formally write the constraint satisfaction problem, set of variable, that is x1, x2, x3, domain d1, d2, d3, any number of domain, constraint, and the constraint Ci can be the cross product of the domain values. Denotes the possible valid joint assignment for the variables. This goal, find an assignment to all variables. Find an assignment to all variables that satisfy all the constraint. So find an assignment to all the variables, x1, x3, x5. What is the assignment? Whether should I choose north or south or east or west? For x1, similarly for x3, similarly for x5. So I need to choose the values of x1. I need to choose the values for x3. I need to choose for the values for x5, which will satisfy all the constraint to track my target. That is the goal. Find an assignment to all variables that satisfy all the constraint. That's why this is called constraint satisfaction problem. We are not optimizing. We are not optimizing. We are saying it is a satisfaction problem. the same constraint satisfaction problem can be treated as constraint optimization problem if for each of the assignment, if we associate some values. For each of the assignment, if we associate some values, then we will say, and the sum of the values should be always maximized. Then we will say it will be constraint optimization problem, and our objective is to optimize, maximize the payoff. Then that's the same constraint satisfaction problem will be treated as a constraint optimization problem. I will be coming to that. Now, model the problem as MAX-CSP, maximum constraint satisfaction. We need to choose those sensors with their values such that the maximum number of constraints can be satisfied. For example, we want to satisfy this one and this one. So we need to choose all the values. X1 should be south, X3 should be west, X5 should be north, X2 should be south, X4 west, X6 north. So through this, we can maximize the number of target we are covering. So you see, anyhow we cannot track the 4 targets at a time. So maybe first 2 we will track those 2 targets. Then in the next iteration we may track this 2 target. So find an assignment to all variables that satisfies maximum number of constraints. Here you see the term maximum number of constraints. So both the targets are satisfied. This one and this one. That means there are 4 targets. Out of the 4 targets, we satisfy 2 targets. But for earlier case, we satisfy only 1 target. So from constant satisfaction to this is constant satisfaction, we are moving to maximum MAX-CSP. Find an assignment to all variables that satisfies a maximum number of constraints. Now, constraint optimization problem. For each of this assignment, we will put a values. If we put the values as infinite, if it is an invalid assignment, then we put infinite. And if it is a valid assignment, we will put 10. We can say it is a constraint optimization problem. We choose that assignment which will minimize my cost. So the same problem can be called as a constraint optimization when we will associate some amount of cost associated with it. Here we wrote as SAT, satisfied, whether this particular assignment is satisfied or not. This particular assignment is satisfied or not. This particular assignment is satisfied or not. But for this case, we are associating a cost. This particular assignment is associated with a cost. Infinite. Why it is infinite? Because for this particular assignment, north, the target will not be covered. So it is an infinite value. North, east, this side. So again, the target will not be covered. It is an infinite value in this way. But for this particular value, south, X1 is south, X3 is west, X5 is north. That gives a value 10. We are putting a valid operation, valid assignment as 10. So constant satisfaction problem can be treated as maximum constant satisfaction, which is optimized. Objective is to maximize the constant satisfied. Maximum number of constants should be satisfied. So MAX-CSP. Next, you have constraint optimization problem, COP. When we say constraint satisfaction problem, there is no question of soft constraint. Either it will be 0 or 1. But when we say about constraint optimization problem, then along with this hard constraint, there should be some soft constraint, which will optimize the value. In the last lecture, I told that the term hard constraint and soft constraint, one of the example I have given that for meeting scheduling problem. You want to schedule a meeting in the department, and there are many people in the department who may have different other meeting. The hard constraint is 2 meetings should not be overlapped. 2 meetings should not be overlapped. 2 meetings of the same person should not be overlapped. That is a hard constraint. The soft constraint is each person may have some preferences. I prefer to have meeting in the first half instead of second half. So that is my soft constraint. But I can attend the meeting in the second half. I don't have any problem. But I prefer. So that can be said as a soft constraint. On the other hand, the hard constraint is 2 meetings of the same person cannot take place at the same time. Then the person cannot attend the 2 meetings. That is a hard constraint. So, constraint optimization problem. Imagine that each sensor is controlled by an autonomous agent. Here you see, in earlier case, we did not consider the concept of agent. Now you may have the question. You may have the question that why are you bringing the use of agent here? It's a very common question people may ask. The idea is, if you treat the problem like this way, we are treating that this is a centralized problem, centralized scheme. Why? Here we are thinking that each of the sensor, each of this sensor, they are taking as a values, everybody knows everybody's values. But in reality, that is not possible. There may be hundreds sensor distributed across in a particular region. Now, what values a sensor is taking, that is immediately not known to all the other sensors, because each sensor is a separate entity. So what we are treating as a centralized notion, that is not realistic. The realistic is the distributed notion. And when you talk about the distributed notion, then there is a concept of agent. That is, each sensor is controlled by a separate system. Each of these sensors is controlled by an autonomous agent. It can choose what values to take, whether it will choose the south, west, north, east. How should this problem be modeled and solved in a decentralized manner? So first you need to model the problem in a distributed approach or decentralized manner, and then you need to come up with some algorithm which will solve the problem. So again, I'm telling you, the idea is distributed approach, not the centralized approach. When we say centralized approach, that implies that there will be somebody who knows or who has the information of all the sensors, which is practically infeasible. That's why we are moving to distributed approach, where each sensor is treated as a separate autonomous entity called as agent, who can choose their own values. So an agent is an autonomous system, interactive, reactive, proactive, that we have discussed. So this is the main problematic. I mean, how the problems of multi-agent system are categorized. It can be constraint programming or constraint satisfaction problem. That can be constraint satisfaction. That can be constraint optimization. When you talk about the satisfaction, then just this constraint satisfaction will be there. When you put some kind of optimization value, then the same problem will be modeled as constraint optimization problem. Then you have DEC-MDP, decision theory. Then you have game theory. There is also where we can use a multi-agent system. Okay. So imagine that each sensor is an autonomous sensor, and how this problem will be solved in a decentralized manner. Now, along with the sensor, this X1, there is one more term associated with it as A1. So A1 is an agent. A1 is the agent who is responsible for choosing the values of X1. A3 is the agent who is responsible for choosing the values of X3. X5 is the agent who is responsible for choosing the value of X5. A2 is the agent responsible for choosing the value of X2. A4 is the agent who is responsible for choosing the values of X4. Similarly for A6. What value they are choosing, for example, A1 is choosing a particular value, and what value A1 is choosing for X1, A1 will send that message to its neighbor, because the neighbors are connected with each other. The neighbors are connected with each other. So if I say the neighbor of A1 is A5 and A3. So after choosing the values of X1 by agent A1, A1 will send a message to A5 and A3 that I have chosen this value, maybe north or south or maybe west or east. So A1 will say A3 and A5 that I have chosen north as my value for X1. Similarly, A5 will choose a particular value for X5, and whatever value it will choose, that will send as a message to A1 and A3. So how DCOP? So we are moving from centralized approach to distributed approach, or rather constant optimization problem to distributed constant optimization problem. So far we discussed constraint optimization problem. Now we are coming to the formalization of distributed constant optimization problem. This is an agent set denoted as capital agent, which is set of agent A1, A2, A3, dot AN. There is a variable X. It can be X1, X2, X3, dot. Domain D1, D2, D3. Constraint, mapping of variables to agent. You have to map. So agent A1 is responsible for choosing a particular value from the domain for X1. X2 is agent A2 is responsible for choosing a values from this domain for the variable X2. A3 is responsible for choosing the values of D1, D2, D3 from this domain for in this way. What is the objective? The objective is find an assignment that minimizes the sum of the cost of all constraint. So here you see we use the term optimization problem. Here you see the term we are using minimization. So here the optimization is we want to minimize the cost. Moreover, find an assignment that minimizes the cost, minimizes the sum of the cost. Mind it, the term is sum. because each agent is choosing its own value. Each agent is choosing its own value. A1 is choosing for x1, A2 is choosing for x2, A3 is choosing for x3, A4 is choosing for x4. So for each choosing, there is a cost associated with it. We have to find out the assignment that minimizes the sum of the cost. No. That minimizes the sum of the cost for our constraint. So, so if you recap the definition of agent or multi-agent system, in contrast with object or entity, when we say agent, they are goal directed. I told they are autonomous. They do task for some objective. Here the objective is to minimize the sum of the cost for an assignment. So what we discussed yesterday, the definition of agent and multi-agent system, how that relates to DCOP, you just see. Find an assignment that minimizes the sum of the cost of all the constraint. So I told you that agent is goal driven. They are proactive. Of course, reactive and social are there, but along with social and reactive, they are proactive. Proactive means I have some goal in my mind. For that goal, I am doing this task. So here, the agent's goal is to minimize that cost. I told that agent is a social. Agent is a social. A1 is interacting with A3. A1 is interacting with A5. They are their neighbor. Just like in the human society, we interact with each other in the society. I have a good relation with my neighbor. I have some connection with another neighbor. So we have the society. In the society, to live peacefully, we have a lot of interaction among the society member. In the same way, the agent needs to talk with each other. They need to interact with each other, with their direct neighbor, to achieve their goal. So each agent is social. Each agent is proactive. Proactive, they are goal driven. They are social because they are interacting with their neighbor to minimize the total cost. So that's why we are moving from constraint optimization problem to distributed constraint optimization problem. So if you have any questions, I mean, the entire discussion is very conceptual, I think, nothing to remember as such. So if you people have any questions, student, faculty, I am ready to discuss. Mr. Bhaskar.
Yes, sir.
Sir,
I have one question, silly question, sir.
Yeah, no problem.
These domains you have chosen, east, west, and north and south.
This is for example. This is for example,
no?
Yes.
Yes. Okay.
So
okay, that depends on the problem where we have
exactly. So this depends on the problem where you are modeling, right? Okay, for this particular problem, we are choosing the sensor. So a sensor can either view its north, it can view its south, it can view its east, it can view it west. So an agent is responsible to choose the values of that x1, whether it will choose north or south or east or west. So that's why the domain will be east, west, north, south. Maybe for graph coloring problem, it will be the number of color, maybe red, black, green. Okay.
Rest is okay with me. And do you have any problem? Anyone you can ask.
Yesterday I have discussed also the same. In fact, one of your student asked me, sir, what is graph coloring problem and how? So I feel as students as well as faculty, all are computer science background. So definitely graph coloring problem is a very common problem for all of us. We are very much familiar with the graph coloring problem. But how the graph coloring problem, traditional graph coloring problem is different with the distributed graph coloring problem, that we need to understand. So I discussed yesterday. Still, if people have any doubt about the traditional graph coloring problem and distributed graph coloring problem, I will be happy to discuss once more. যদি কারোর কোনো রকম কোনো কোশ্চেন থাকে distributed graph coloring নিয়ে, so I will be again happy to discuss why we are moving from centralized approach to distributed approach.
Okay, anybody have any doubt? I think, sir, you can.
Okay. We discussed this diagram: MAX-CSP, constant optimization, hard constraint, soft constraint, and minimize the cost. So all the three, whether it is a constant satisfaction problem, whether it is a MAX-CSP or COP, all can be modeled as D for distributed. We can have constant satisfaction problem, we can have maximum constant satisfaction problem, we can have constant optimization problem. All the three problems can be modeled to DCOP, distributed constraint optimization problem. In general, distributed approach is more appropriate than centralized approach. When you go for centralized approach, the entire design is centralized to a particular node. If somehow that node fails, your entire system will be failed. If you go for centralized approach, somehow there is a problem in the network, the entire system will be collapsed. So always better to choose distributed approach rather than centralized approach. But when you choose for distributed approach, along with the time complexity of the algorithm, you need to associate one more term that is called message passing complexity. When you go for centralized approach, there is no question of message passing between the nodes. But when you go for distributed approach, there will be a notion of message passing. And along with the time complexity, you need to put one more performance metric, which is message passing complexity. So when you talk about DCOP, there is a notion of agent. So variables are controlled by agents. The values of the variables will be controlled by agents. Communication model, you need to choose proper communication model. Otherwise, it will be a communication overhead. The message passing overhead will be very high. Each agent only knows its local knowledge. That means a particular agent knows the color of its own and the color of its direct neighbor, not the entire knowledge. I told you in the first class, somebody asked me that what is accessible, inaccessible. Here, agent A1 knows only the color of X1. Maximum, it can know the neighbor's color, not the entire world. So a part of the environment is accessible to A1. A part of the whole environment is accessible to A5. A part of the environment is accessible to A3. For example, I'm giving you a real example. Sitting at Durgapur, I can tell that the weather is cloudy and the weather is a little bit cold. But sitting at Durgapur, I cannot say the weather of Ramgarh, because the weather of Ramgarh is not accessible by my body. I have to ask somebody. And whenever I ask somebody, I need to send some kind of interaction and message passing. But for Durgapur's weather, I don't need to ask anybody because I am staying itself in Durgapur. So as right now I am in Durgapur, I can easily, if I need to know, I will just open my window, I will see the weather, I can understand the weather of Durgapur. But I cannot know the weather of Ramgarh. To know the weather of Ramgarh, I have to call somebody who is staying in Ramgarh. So I need to go for message passing. So the entire, though I'm an Indian citizen, but the entire country is, the weather of entire country is not accessible to me. My body can access only a part of the country. So that's why distributed system is more realistic than of centralized approach. Why distributed approach? Natural mapping of multi-agent system. Potential faster by exploiting parallelism. Potential more robust, no single point of that we discussed. No single network bottleneck. Maintains more private information. Each agent maintains its own private information. So now we will be discussing some of the algorithms for solving the DCOP problem. So this is the complete categorization of the DCOP algorithm. There can be two types of algorithm for DCOP. One is the complete algorithm, another is the incomplete algorithm. What is the difference between the complete algorithm and incomplete algorithm? The complete algorithms are the algorithms which give you the optimum result. The most optimized result it will provide. So if you end up your algorithm with the termination, then you will get the most optimal result. That guarantees for complete algorithm. But when you go for incomplete algorithm, you may get optimal result, you may not get an optimal result. Your result may vary over the time. In one iteration, you may get a good result. The next iteration, you may get a better result, or you may get a more worse result than the earlier result. Now, inside the complete algorithm, it can be partially decentralized, it can be fully decentralized. Decentralized means distributed. It can be synchronous, it can be synchronous and asynchronous. Synchronous can be search and inference based. Similarly, desynchronous can also be search and inference based. Asynchronous can be of search. Similarly, for this one also is a fully decentralized. This fully decentralized can be of two types: synchronous and asynchronous type. What are the metric? I don't know whether you are habituated with the term metric. The metric is something like which tells you how good or how bad it is. We can say your CGPA, semester credit point average, is a metric to say who is topper, who is second topper, who is third topper in your batch. So CGPA is the metric. NIRF rank is a metric to rank a particular university or particular college in India. QS ranking is a metric to rank any university or college in the whole world. So these are called metric. CGPA is a metric. Percentage of marks is a metric. So what are the metric? Metric is agent complexity, that is the time complexity. Network load, that means message passing complexity. Message size, per message, what amount of information it will carry, that is called message size. So agent complexity, network load, message size. Mind it, I am repeating once again. When you talk about centralized approach, these two terms, that is network loads and message size, will of no use. When you talk about centralized approach, there is no question of network. When you talk about centralized approach, there is no question of message. So these two metrics will not be of use. But of course, time complexity will be there. So time complexity will be there in centralized approach as well as distributed approach. But along with time complexity, there will be two more complexity in distributed approach. One is the network load or message passing complexity, and the third one is message size. Incomplete algorithm. It is any time, in any iteration you can ask for the result, but there is no guarantee of the quality of the result. You may get a good result, you may not get a good result. That's why there is one more metric, execution time versus solution quality. How much time you execute and what quality of result you can get. So when you talk about the synchronous system, obviously people are familiar with this term. Then each agent will wait for some kind of wait and signal for other agents information. So a second agent will start its work only the intervention of the first message, first agent kind of thing. So there is a synchronous approach. And another is asynchronous approach. Each agent can work at its own without thinking of the other agent. So the first algorithm that we will be discussing is synchronous branch and bound. So under the DCOP algorithm, we will be discussing synchronous branch and bound algorithm. Let us take an example of graph coloring problem. This is a small graph A, B, C, D. These are the arc of the graph and these are the node of the graph. And they are undirected in nature. Now there are two variables, xi and xj. As there are two colors, so possible combination can be red, 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 green, green, red, like this way. So these are the possible combination. If A and B choose the red color, both are red color, then the cost will be 5. If A and C, A choose red, C choose red, then the cost is 5. BC, if B choose red, C choose red, then is 5. BD, B choose red, D choose red, is 3. Next, xi, xj, ab. If A choose red and B choose green, then it will be 8. If A choose red, C choose green, then it will be 10. AC, AC, 10. Similarly for BC, 4. Similarly for BD, B choose red and D choose green, it will be 8. Like this way. If both AB choose green, green, 3, AC choose green, green, 3, BC choose green, green, 3, BD choose. So this is given. What is the objective? How do we solve this distributedly with minimum cost? So we have to assign the color to each node. We have to assign the color of each node with minimum cost. That is our objective. We have to assign the color of each node with the minimum cost. Okay. So Mr. Bhaskar, whatever you asked, here you see the domain value will be 2.
Yes, sir. Yes, I got it, sir.
So here you see there are there are 4 variables, A, B, C, D. We can put agent. Maybe agent A1 is responsible for choosing the color of node AO. Agent A2 is responsible for choosing the color of B. Agent C is responsible for choosing the color of C. Agent D is responsible for choosing the color of D. And there are 2 colors. So a variable can have 2 domain value, either red or green.
Yes, sir.
So at the end of full iteration, we need to get the values of all these variables A, B, C, D such that the total cost will be minimized. That is our objective. So make an order first. This algorithm works like this way. It is a complete ordering. Agents operate on a complete ordering. Agents exchange in messages of partial assignment, CPA, containing partial assignment. When a solution is found, its solution cost as an upper bound, UB, is broadcasted to all agents. The upper bound is used for branch pruning. I will be discussing what is the meaning of this thing. So this is my complete ordering A, B, C, D. So this way we will try to prune. This is my starting node with 0. I mean null. Nothing is there. Either A can choose red or A can choose green. Either A can choose red or A can choose green. If A choose red, B has again 2 options. Either B can choose red or B can choose green. If B choose red, then again there are 2 options. Either C can choose red, C can choose green. If C choose red, B can choose 2 options. In this way, we need to prune. Now here again, I am repeating, some of you may have the question that is it traditional graph coloring problem? No. Traditional graph coloring problem, the constraint is no 2 adjacent node have the same color. But here we are not considering that type of requirement. Here, any color can be chosen, but for that associated value will be there. So first choose this the null node, the root node, as upper bound with an infinite value. Sorry. UB as infinite. Choose A as red. If I choose A as red and B as red, then what will be the value? If you see the table, A red, B red, the value is 5. If A red, B red, the value is 5. A red, B red, the value is 5. Then after choose B as 5, C can choose either red or green. If C choose red, then what will be the total cost? If C choose red, what will be the total cost? You see, that means AB is red, BC is red.
So BC reasons are 10 is there, I think.
দেখো ওটা ভেবে
10 is there and 10 plus 5, that's the same thing.
No.
That yeah.
No.
BC is 4. Okay.
Can anybody say what is therefore if you're interested, you can put this table in somewhere in your paper on pen and paper, then it will be easy to check.
Yes, sir, yes, sir. I like that.
Those who wants to do with me, you can draw this table and the graph in your pen and paper, then we will be iterating the diagram solution. You just, instead of putting the color, you give the name: red red, red green, green red, green green, and the values, this particular table. Then it will be easy for me to make it clear for you. Here you see A is red, B is red, the value is cost is 5. B is red and C is red, the cost is লিখলেন আপনি?
Yes, sir. I got. I have written.
A is red, B is red. What is the cost? 5.
I got it. Yes, sir. That is okay.
A is red, B is red. The cost is 5. B is red and C is red. The cost is again 5.
Again 5.
So it should be 10. It should be 10, but we are writing 15 because in this assignment, A is red, B is red, B is red, C is red. Along with that, there is one more assignment: A is red and C is red. That also we need to consider. AB red 5, BC red 5, and also we are having AC red. So the associated cost will be 5. So 5 plus 5 plus 5.
Sir, because the direct connection is there, that's why I am taking.
No, because the assignment is there, we are putting the values for the assignment. We are putting the cost with the assignment. আমার কাছে তো এই টেবিলটা দেওয়া আছে, So whenever I find that AB is red, we will put value 5 cost. Whenever we will get AC red, we will take the value as 5. Whenever we will get BC as red, we will put the assignment cost is 5.
Okay, sir. Okay,
whenever
sir.
we have red with the BD, then 3. So here you see with this assignment, we have this one is red, A red, B red 5, B red, C red 5, and again A red and C red. So 5. So it becomes 15. Now here you see we are considering CD, but there was no cost associated with AD and BC. Nay, Arjun 18. Okay.
Okay, sir. Okay, sir. I got it.
So again, now the upper bound becomes 18. Can anybody say why the upper bound becomes 18?
So because the maximum length is maximum cost is 18.
18. So from infinite, it has been reduced to
18.
18. Okay. So if we choose the color for all the values A, B, C, D as red, my upper bound value is 18. Now we will be looking for any further assignment which gives me the lower cost than of 18. If we get any further assignment whose cost is less than 18, then I will choose that. Otherwise, we will discard. Should I choose it? D is 18. Now D can also be green. If I choose D as green, the total cost will be this, and this. It is 23. So should I choose this assignment?
No, sir, because this is minimum, not minimum. 18 is minimum one.
So we will discard. Clear? Next, we can choose the values of C as green. The associated cost will be 19. The associated cost is 19. So again, 19 is greater than 18. We will discard. Next, choose the values of B. 8. Should I choose it? We should, because 8 is less than 18. We will further expand. C can be red, C can be green. C can be red or C can be green. If we choose the C as red, the value is 16. We need to expand, but we cannot. So we will discard, because 26 is greater than 18, and my lower upper bound becomes 18. So in this way, you need to prune the entire tree, and we will be choosing that path only if it gives lower than the value of 18, because my upper bound already I got a value of 18.
Yes, sir.
Now, if any person have any questions, I can discuss it once again. Or if you have questions,
I'm clear.
How we are getting 18 or 16 or 26?
Yes, I got it, sir.
And why we are pruning and discarding this part?
Not an issue. If 18, if I got the less than 18 path, then I will have to choose that one.
That only, because already I got the 18.
Yes, minimum one
to color the entire graph. So why should I choose better larger than that, larger cost than 18. Okay.
Okay, sir.
So in this way, you need to prune the entire graph. We need to prune the entire graph. And you see, even if we choose the other part, that will not give you the better result than of this 18. So what will be my assignment? A will be red, B will be red, C will be red, D will be red. Because for any other assignment, the values will be, the cost will be higher than of 18. So I should not choose. For example, if I choose this, A as green, B as red, C as red, D as red, it will be 48. If I choose A as green, B is red, C is red, and D is green, it will be 51. Similarly, choose this path. A as red, B is green, C is green, D is green, it gives 24. But whereas I have a lesser value, lesser price of that. So obviously I will go for that lesser price. That is the thing. Okay. Now, the metric, the performance metric, as I said, that is, how the performance metric is used. The solution it finds is optimal. Yes, the solution it finds the optimal, because we are searching the entire graph and then we are bringing the result. Is it complete? That means does it terminates or does it goes for infinite loop? Yes, it terminates. Message passing complexity. As I said, that when you go for distributed algorithm, not only for DCOP or whatever, whenever you go for DCOP kind of, distributed algorithms, apart from time complexity, you need to go for another complexity that is called message passing complexity. So here, the message passing maximum number of messages, order of b to the power d, where b is the branching factor. What is branching factor? Can anybody say? What is the branching factor? 2. Number of color. From one node, it can be either red or green. From another node, it can be red or green. So branching factor. Number of variables, that depends on the number of node in the graph. For this graph, the number of variables are 4, A, B, C, D. So message passing, number of message passing is order of b to the power d. Message complexity, maximum size of the message, order of d. D, number of variables, that many values will be here. Runtime complexity, order of b to the power d. These are the okay. Now this algorithm can be parallelized in some computation. That means in some portion you may find that you are getting some parallel values. For example, a typical example of this, that if you go from 10, you will be getting 3 and 8. From 14, you will be getting 3 and 8. Now, if you expand this, if you expand further to that, the branch of this and the branch of this will be same. So you can choose any of the branch and that will give you the result. You don't need to expand both because they are same, independent of the value of this. Similarly, from this, 10 and 3, 10 and 3. If you expand this one and if you expand this one, the remaining branches will remain same. So just expanding one will be sufficient to prune the graph. Okay, so I think this much is sufficient for today. Next class, I will start with the pseudo tree, another. What do you say?
Yes, sir. Not a problem, sir. As I wish.
দেখুন আপনাদের যদি কিছু বক্তব্য থাকে আমি আবার বলতে পারি বা স্টুডেন্টদেরও কোনো জায়গায় যদি পড়ার থাকে।
Okay, students, anybody have any doubt, please ask again. Sir can discuss, and otherwise we can finish that. Any doubt, please ask the question.
Or the faculty members if they want to discuss.
Yes.
Hello, sir.
Hello.
Good morning, sir.
Good morning.
Sir, everything is very clear. The way you are explaining everything is
Speak
very
loud.
clear.
Yeah, please loudly. Yeah.
Sir, but the topic is very new for us.
Okay.
Okay. I think that's why for me it is very new. मेरे पास ज़्यादा क्वेश्चन ही नहीं है कि मैं उसमें पूछूं और आप बहुत अच्छे से समझा भी रहे हो हर चीज़। तो बोलना एक रिक्वेस्ट है आपसे कि यदि पीपीटी अभी अवेलेबल हो जाता तो फिर हम चीज़ों को खुद से भी रिवाइज करने की कोशिश।
Sure. Just I am forwarding. Just wait. I'm giving it to your HOD.
Yes, sir. I will give it.
Just wait. I'm giving it to your HOD, and I will request you to please forward the PPTs.
Yes, I will forward that one, sir.
This one, this COP.
Thank you, sir.
Yeah. So you go through the PPTs. If you have any doubt, you please let me know tomorrow, and day after tomorrow I will be available. Okay. So, Oscar, দেখে নিন আপনি।
Okay, sir.
আমি পাঠিয়ে দিলাম। হ্যাঁ, আপনি একটু আপনার স্টুডেন্ট মানে গ্রুপের মধ্যে ডিস্ট্রিবিউট করুন।
একদম স্যার। Yes, surely I will give. Surely.
তো আমি অলরেডি পাঠিয়ে দিলাম। হ্যাঁ, তো তোমরা দেখে নাও। যদি if you have any doubt, tomorrow again we can have a discussion. ঠিক আছে?
Again, sir.
Okay. So it is not the thing that today whatever I discuss, tomorrow I won't discuss. So if you have any doubt after the PPTs, we can have again discussion.
Okay, sir. Sure. Okay, sir. Then should I stop today?
Yeah. Okay. Thank you.
Okay. Thank you, sir.